Hello everyone, we are back to continue our discussion on the ICP. In the last class I had shown you different types of sample introduction systems, and I had also talked about the peristaltic pump for sample introduction. So, I am going to show you the same slides a little bit more quickly, and we will proceed ahead with our program. So, the sample introduction means the most common means of sample introduction is through the Bernoulli effect, that is high velocity moving gas flowing around a capillary sucks the sample and delivers it at the tip. Here the liquid breaks down into fine droplets before entering the plasma. Another way of introducing the sample is to pump it through a capillary using a peristaltic pump. At the tip, the high velocity argon flows across at right angles, causing the same Bernoulli effect. So, it is also possible to atomize a sample in a graphite tube and introduce the vapor into the plasma. So, I had shown you the bottom figure in the here. This is the how we introduce the sample through a peristaltic pump. Okay. So, peristaltic pumps, I had shown you this figure, I had told you that there will be bearings around which a tube is going round and round, one below, one above, one below the bearings, and the tube carries the sample through a conical flask, and here you can see the principle of the sample introduction using a peristaltic pump. Here these are all ball bearings, you can see these black systems on the top. Here you can see near the top there is a ball bearing, there is one more ball bearing here, there may be more also. So, these are the three different systems where the three different stages where the liquid is sucked in and delivered. For example, in the first figure on the top, you can see that the sample is moving here, it gets squeezed inside the between this ball bearing and the tubing, outer tubing, and then the liquid gets sucked, and as this ball bearing moves, the liquid will be sucked inside and then it will be flowing through. This is the second stage where the ball bearing has moved slightly to the left and liquid will move to the right, and same thing. So, now the liquid has been sucked up to this point, and then in the third stage when the ball bearing moves like this completely, the liquid will be sucked like this and then it will be going through the peristaltic pump. The advantages of such a peristaltic pump is that the sample does not come into contact with the metal parts of the peristaltic pump. I do not know how many of you are aware, generally pumps are used for the delivery of liquid. It can be anything, it can be a submersible pump like a borewell what you might have heard, or it is meant for transferring liquid, alkalis, acids, etc., which for which the samples are hazardous in nature. So, the use of pumps in all spheres is very well known. So, these pumps have a characteristic that some of them are positive displacement pumps, some of them are negative displacement pumps. So, most of these pumps operate in contact with the liquid. For example, if you want to suck a sample from a borewell, you need a submersible pump in which the pump will be pushing it up and down, so that the liquid will be coming out. So, there the submersible parts, pump parts are in contact with the liquid, that is borewell water. So, if it is acid, then you can use special materials, because rubber and other tubings will not work, because acid will attack the rubber. So, sometimes we use PVC pipes, and sometimes we use Teflon pipes, sometimes we use stainless steel, like that different components are introduced in the pumps. But in peristaltic pumps, the liquid does not come in contact with any of the metal parts. That means the contamination is minimal here. That is required because we are going to determine many elements at parts per million or parts per billion level, parts per trillion also. So, any small contamination and can disrupt the result. So, the one has to be very wary of contamination, and for this purpose a peristaltic pump is used, and this peristaltic pump is also used in our day to day life, where the people with diabetes undergo dialysis. For example, if blood has to be taken out from a body and then re-put inside the body again, then we need a peristaltic pump, because we do not want the blood to come in contact with any of the external agencies like air, water, metal parts and many other things. So, this is how the peristaltic pump works. The principle is very same, very nice. So, this is the working principle of a peristaltic pump. They are positive displacement pumps used for pumping a variety of fluids. The fluid is contained within a flexible hose or tube, which I had shown you in the previous slide, inside the pump casing. So, actual pumping principle is called as peristalsis. That is based on alternating compression and relaxation of the tube, drawing content in and propelling the product away from the pump without coming directly in contact with the sample. So, a rotating shoe or roller passes along the length of the hose or tube, creating a temporary seal between the suction and discharge sides of the pump. You can see here in my previous slide, here there will be expansion, there will be compression, there will be expansion, there will be compression. Like that, there will be a succession of compression and expansion. And so, as the pump's rotor turns, this sealing pressure moves along the tube. Okay. So, the sample gets sucked in and then moves without coming in contact with the pump. So, the tube or the hose forces the product to move away from the pump and into the discharge line. So, such peristaltic pumps are available in the market, and they have been adopted in analytical science, because an automatic sample delivery system ensures a trouble free chemical analysis. So, very small size pumps are available in the market. So, the pressure in the hose gets released and the tube recovers, creating a vacuum. Normally, what happens is, when the bearings compress, liquid will get sucked in. So, after some time bearings will move away and then liquid will be pushed out like that, and thereby how does it get pushed out? Because of the vacuum. It generates a small quantity of vacuum through which the liquid will rush in through the tube until the delivery point. So, this draws the product into a suction side of the pump, and that is the priming mechanism. So, once the pump is primed, you will not even feel that the sample is being sucked and then expanded, vacuum created and all these things. So, combining these suction and discharge principles results in a powerful self priming positive displacement action, that is peristaltic pump for you. So, you have to be very careful when you want to buy a ICP AES, because the sample should not come in contact with the metal parts of the pump. So, the sample material for excitation has to be carried out into the plasma by means of the central gas flow, the injector, that is called as injector gas flow. All this I have covered earlier, except for the working principle of the peristaltic pump, I had covered most of this. So, in the most usual arrangement, the sample is in the form of aqueous solution, and that is partially converted into fine droplets by the nebulizer. So, it is an aerosol of these fine droplets in argon that is injected. That means, the argon is used as a media to create an aerosol, because why I am telling you this is the plasma will not tolerate liquid inside the toroidal space of plasma. So, if you inject liquid, plasma will get put off. So, the fine droplets are generated by the argon gas. It is an aerosol of these fine products in argon which is injected. In practice, any particles finer than about 10 millimeter can be transported in a stream of gas without much deposition in the tubing. So, that aerosols of solid particles can also be injected. In addition, material for analysis can be injected in the gas phase so long as suitable volatile compounds can be generated. So, this figure also I had shown you in the last as a last slide in my last interaction with you. The sample is here, it enters the nebulizer, and then there is argon gas coming through. Argon gas is coming axially along with the concentric tubes, and then it enters. This aerosol enters, this liquid enters here near the plasma, and in the plasma toroidal space the sample enters, gets excited to higher energy levels, and then emission takes place, and the emitted radiation is separated by the grating, and which is collected by the detector. So, when I do not have the sample, I do not have any reading at all. Okay. The sample, if I have a blank sample, then there is no reading, but if there is a sample contains the analyte, and then I have some photons coming out of the emission lines. So, in principle the sample can be in solid, liquid or gaseous state, and the gas sampling is a very specialized application by itself. Normally what I expect is the introduction of a sample as a liquid is simpler than introduction of sample as an aerosol, because in analytical sciences most of the time we have been talking about parts per million, parts per billion level analysis only. So, the sample introduction for ICP is basically a pneumatic nebulizer only, okay. And this may be of concentric or cross flow, both designs are possible. So, ideally the nebulizer should generate droplets of about 10 micrometer in diameter for efficient transport into the plasma. Suppose the particles are bigger, then what happens? If the particles are bigger, they will not form the aerosol, but they will fall down, and the water droplet, it will drain out, that is waste of the sample. So, the more sample is introduced as an aerosol, we have a better sensitivity. So, the droplets, fine droplets need to be collected as aerosol, bigger droplets need to be removed as a waste. So, the transport efficiency, what we call the conversion efficiency of the sample into aerosol, that is analyte mass that reaches the plasma compared to the analyte mass aspirated. Suppose I inject 5 ml and all the 5 ml does not form aerosol, it will form only about maybe 1 ml or about 13 to 20% is the efficiency. Whatever is the liquid you take, you want to make an aerosol, about 13% gets into air and remaining becomes bigger droplets and needs to be drained out. So, that is usually below 2%, and sometimes it goes even less than 1% of the total liquid introduced. That means, if you introduce about 100 microliter, only about 1 microliter gets converted into aerosol, maybe 2%, maybe 2 ml out of 100 ml. So, this value compares unfavorably with about 10% transport efficiency, that is achieved by atomic absorption spectrometry. Why? See, the point is, in atomic absorption spectroscopy, we have the gas flow about 6 liters per minute, 6 to 10 liters per minute. Here in ICP, it is 1 liter per minute. So, the difference is in the efficiency of the sample to be converted into an aerosol. So, the efficiency of a nebulizer, if you have taken the course, you can compare the nebulizer design in AES as well as this. Skoog and other books which I have recommended for reference also show these figures. You can compare how the design of a nebulizer works, and there you can see lot of fundamental difference between the AES and ICP values. But in general, it is not favorable with respect to AES compared to AES. So, this is the Meinhard nebulizer. Here I have the liquid sample coming through, and then obviously we assume that the peristaltic pump is somewhere here, okay. And then liquid sample input is there, it enters the capillary, comes out, and there is a shell here that creates one more tubing, and argon gas input is from the bottom, and it goes like this. So, the gas flow rates used vary substantially, but for other outer flow 10 to 20 liters per minute of argon would be used. For example, the inner carrier flow should be approximately about 1 liter per minute, which I had already mentioned, and for the intermediate or auxiliary flow 0 to 1 liter per minute also is fine. So, the frequency of the radio frequency of generator might be in the 27 to 56 megahertz range. These are all technical details. You will find most of these details in your in the instrument manual. In general, they will recommend what should be the flow rate, what is the megahertz range radio frequency generator, and all that will be mentioned in the literature or the menu card of the instrument manuals, operating manual. And for all argon ICP, a typical power input would be in the range of 1 to 1.5 kilowatt per kilowatt. That means, the power required to put the sample into the toroid space of the plasma is about 1 to 1.5 kilowatt. So, the region of the tail flame observed for analytical work is usually a 4 mm vertical window from some 10 to 20 millimeter above the coil. Usually, if I remember this, that means the plasma will extend approximately 20 millimeter, but the sample measurement needs to be within 4 vertical window. So, the benefits of ICP stem not only from the very high temperature of the source, but also the unique method of heating the sample, that is ICP for you. So, a typical plasma appears as a very intense white flame. It has a non-transparent core topped by a flame like tail. The core extends a few millimeter above the tube and produces the atomic spectrum of the argon superimposed in a continuum spectrum. So, this sentence I want you to understand carefully. What I am saying is the non-transparent core is like flame-like tail of the plasma. So, the core extends a few millimeter above the tube and produces atomic spectrum of argon also, as well as the superimposed in that argon emission line. There will be, if our sample is introduced as an aerosol, the argon also gives out emission lines and the sample also gives out emission lines. Water vapor is there. So, hydrogen and oxygen and several other things, they also decompose around 10,000 degree centigrade or Kelvin. So, they also emit radiations. So, you have to choose which is the correct analytical line, emission line for each element you want to determine. Otherwise, the whole spectrum if you see in an ICP, what you will see is the combined spectrum of oxygen, hydrogen, water and then the sample and argon. And argon line would be very intense because our argon flow rate would be approximately about 20 to 30 liters per minute. For sample introduction 1 liter per minute, but the remaining argon also gives out a fantastic spectrum, that is a continuum spectrum. From that continuum spectrum there will be superimposed lines for different elements. So, we have to pick up only that line. That means, whatever line wavelength you choose for the estimation, there will be certain amount of argon emission associated with that, that is background. Okay. So, the background is of that of argon and the spectrum is that of continuum spectrum. So, this continuum spectrum is typical of the charged ions and electrons interaction, and that is known as Bremsstrahlung. This Bremsstrahlung is nothing but a sort of additional lighting, additional spectral feature coming from argon. It is a German word, Bremsstrahlung. Strahlung means radiation in German, Brem means external, additional. So, this is known as Bremsstrahlung. So, there is no typical English equivalent for this, because sometimes most of the ICP work was done in Germany, development work for analytical applications. So, that name has stuck as Bremsstrahlung only. So, about 10 to 30 millimeter above the core of the continuum, 10 to 20 millimeter above the core, the continuum argon radiation fades away. That means, it becomes very less, and the plasma is optically transparent. That means, you will have very less Bremsstrahlung for the system. So, the spectral observations have to be made about 10 to 20 millimeter above the induction coil, so that the temperature of about 6 to 8000 Kelvin should be available there. In this region, the background radiation is remarkably free from argon lines, that is good for us, but those of calcium, cadmium, chromium, manganese, nickel, iron, whatever element you want to determine, they remain available to us to choose for the emission monitoring. So, this is how the temperature varies in the plasma. So, what do we see here? We have the concentric tubes here. This is the plasma height above the load coil, that is, these are the load coils. Here you can see 2 round circles where my pointer is here and another is there. So, it is a circular feature that is for RF, and sample introduction comes through the tubing, and the plasma, general shape of the plasma is like this, okay. And the argon gas will be flowing through all these concentric circles, and the plasma will be available slightly above this. So, approximately near the plasma, near the tip of this thing, we have temperature of about 10,000 degrees. At this temperature, Bremsstrahlung would be very high, and then you go slightly up, temperature is around 8,000, and then 6,800, 6,500, around 15 millimeter, the temperature of the plasma will come down from 10,000 to 6,500. Go for by another 20 millimeter, go by another 5 millimeter, up to 20, the temperature prevailing will be approximately 6,200 Kelvin, and still above around 25, the temperature will be around 6,000 Kelvin, and this temperature will constitute approximately 10% of the total radiation that is coming out. And this is how you may say, why not measure it here itself around 10,000 or 8,000, but in general it does not make much difference, because only around 6,000 degree Kelvin range we make the measurement, because Bremsstrahlung will be less. Moreover, many of the analytic samples do get vaporized and start emitting radiation around 6,000. Suppose some elements do not, then you go down, measure it around 15 millimeter, that will be around 6,500, or you can go still nearer up to 8,000 you can measure, but the background radiation will be much more. Okay. So, the temperature profile within the ICP flame, which I showed you just now, at different heights I have shown in the figure. The ICP method of heating offers a much better chance of avoiding the self absorption, and self reversal also effects are also very minimum, unlike atomic absorption spectrometry. So, the main problem with ICP with AES is that the signal gets reduced because of self reversal. That means the ions generated, atoms generated also absorb the same radiation that is coming out. So, this self reversal, that is absorption of the same radiation what is coming out is a little bit of a problem that reduces the calibration quality, and it also introduces some sort of a curvature in the when you do the calibration curve. So, we want minimum self reversal. Fortunately, it works so in ICP, inductive coupled plasma atomic emission spectrometry. So, for quantitative emission efficiency, it is assumed that the emitted energy is proportional to the concentration of the atoms or ions. Why? Self reversal is minimum. That is why we should assume that the proportion of the emitted radiation is in 1:1 correspondence with respect to that of atoms or ions. Some of the emitted photons will be absorbed by the same emitting atoms or ions, and in consequence the observed radiation will be reduced. Okay. This in turn will destroy the proportionality between the element concentration and the light emitted. I urge you to go through this slide more carefully, try to understand the ideas. If you have any doubt, you can write to me and I will be able to help you out with understanding of the subject much better. So, this is another profile of the plasma. Here what I am showing you is approximately 10,000. It also extends not only vertically, but also horizontally above the tip. Okay. So, this is how the moment here it is 10,000, here it is 9, 7, 8, 6,000 etc. that is near the edge about 25 millimeter above the plasma. So, the profile how the temperature varies across, not vertical, but across are the profiles shown here, and when the sample is introduced there will be a dip in the temperature. That is how the sample introduction, sample should be as less as possible. Okay. But the temperature comes down drastically the moment where the sample is being introduced. You can see the big dip here, and above this the dip is very less, here it is still less, here it is almost non-existent. So, approximate temperatures in degree Kelvin in ICP flame, and cross sectional view also I am showing you. I may ask you about this in the examination if you are taking a test. So, now I would like to tell you about the advantages of plasma source. So, coming back to our discussion about why ICP AES compared to atomic absorption, that is an eternal debate I think. Okay. So, the main advantage is high temperatures ensure complete atomization. So, fewer interferences are found in ICP. Why? Because high temperatures ensure complete atomization. So, atomization occurs in a chemically inert environment. This is another advantage. So, temperature cross section is more uniform above a 15 mm, and therefore, self absorption or self reversal do not occur. This point I have conveyed to you so many times now. Hence, calibration curves are linear over several orders of magnitude of concentration. I had earlier mentioned to you that whenever we want to make a calibration curve, we work with 10 ppm, 50 ppm, 100 ppm, 1000 ppm like that. It is not in arithmetic progression 1, 2, 3, 4, 5 or 10, 20, 30, 40, no, not like that. So, 20, 40, 60, no. What is required is 10, 50, 100, 1000 like that you can make the calibration curve, but the problem is the curvature, the calibration curve may be a little bit curved. Since the plasma produces significant ionization, it is an excellent source for ICP MS also. So, typical characteristics of plasma source spectrometers is that the resolution for the wavelength is 0.01 nanometer, or the delta lambda to delta lambda ratio should be more than 100,000, and computer is there, then things are automatic. So, the rapid signal acquisition and recovery is another advantage. Stray light almost nil, because the plasma is transparent. Wide dynamic range, this I have already explained to you. Accurate and precise wavelength identification and selection, that is possible with the help of computer and stepper motors. So, precise intensity readings can be obtained with less than 1% relative standard deviation. So, high stability with respect to environmental charge changes are possible, and computerized data handling makes the ICP operation very simple and straightforward. We will continue our discussion in our next session. Thank you.